messing with electric kilns for a while. Long ago, I first built one to do like glass smelting, like uranium and stuff. So it was a weird shape. This one is kind of more your typical knife making heat treatment kiln, and just thought there seemed enough interest to go through basic techniques of how to build one and the mysteries of how to make it hold the temperature you want. So mostly it's useful for heat treatment of tools, but you can certainly do other stuff, like in glass melting. It dries. It's a great drying oven. You can set the temperature you want, and it'll just do it. So the working limit is somewhere around 1900 degrees Fahrenheit. You can probably push it a bit hotter than that, but then your element burns out fast. So I kind of based, well, pretty much all is based on these insulating fire bricks. This is kind of the main construction material, and the brick module, these guys are 9 inches wide, 4 inches high, and 2.5 thick. And they're quite precise on that dimension, but that's the module, is 9 by 4. And these are all this dry fit in there. So these are the expensive part. Locally you can get them from Kinney Brick Company, and they're about $6.50 each. This uses 20 bricks if you don't drop any, because they are about as strong as a stout graham cracker, which is great because they're insulating. These are the 2300 degree brick. They commonly also come in a 2600 degree variety. Those are a little more durable, but they're also heavier and less insulating, so you'll use up more electricity. So you want the light, fluffy ones. If you go to just any hardware place and ask for fire brick, they're going to give you these like 8-pound, more yellow looking, I don't know exactly what they're made of, but you don't want that at all. That's like a fireplace fire brick. These are insulating fire bricks, or IFBs. So it's good to get them locally. You can order them usually for more expensive than what I've found locally, and if you order them from somewhere, probably half of them are going to show up with chipped corners and breaks. So getting them locally is good, and then it's pretty. They don't have a bunch in stock, so usually it's good to call them ahead and ask.
Can you restate the company again?
It's Kinney Brick. It's down in the South Valley.
Common nomenclature for the different fire bricks are soft fire bricks and hard fire bricks, just to demonstrate some, and they are the difference in weight or the density. But these are fairly easy to carve, and like you said, stiff graham cracker, thus soft fire brick.
So, so these bricks make up the base material. Then the other thing we're going to be using is, this is the resistance wire. It's Cantol. The brand is, I think they call it A1, but that may be the specific alloy. It's basically a chrome and aluminum. It's something like 22% chrome, 6-ish% aluminum, I believe, and the rest iron. So it's kind of like a weird stainless steel. This comes annealed, but it's moderately stiff. The rolls are not too expensive. This one is using 18 gauge wire and 100 feet, which will make you 2 almost 3 coils, but probably 2 elements is about 20 bucks. So it's less than $10 per element if you're rolling it yourself. There are some places where you can buy pre-coiled elements, but they're going to be much more expensive. Then you might be 50 bucks an element. And you can't size it exactly. So a lot of the trick is sizing the element correctly for your volume, for your voltage. There's a couple of, and then, so that's the wire, and we'll go into making the element and shaping the bricks. And then the other thing that everybody probably is pretty familiar with is just fabricating an enclosure. Since that's kind of the easiest thing, I'm just going to show that first. So this is all
16 gauge mild steel that's been sitting in the yard for a couple of years. So I don't have a big bending brake, so the trick for getting nice square corners, you want, because these bricks are pretty precise and it's all dry fitted together, you want a nice tight dimension. If there's a lot of spots, the bricks will wobble around, you'll have gaps, things like that. So this needs to be pretty tight tolerance. Probably need to be less than a 16th of an inch on the inside, where you're going to be sanding fire brick a lot. So the main trick for getting these nice square corners is a little bit of the dark side for fabricating. This is cheese grade circular saw, but this is a metal cutting blade for it. So this is just a woodworking saw. The metal ones typically go to slower RPM. So the main trick is, instead of a 7 1/4 blade, you stick a 5 3/8 blade on it, and that gets a slower surface tip. And then it is less likely to chip teeth or overload your saw. Because here we're only doing really shallow cuts. So if you're trying to cut like metal 2x construction studs, this won't work for it. But for cutting sheet metal, it's perfect. So the main trick is I set the depth to go about halfway through my 16 gauge sheet, and then you run it and cut halfway through. And then, so that's this little score mark here. And you lay it out, and the beauty of this method is then you can put your bend in it like that, just by hand, with a perfect straight corner. And I'll pass this around, those have sharp corners. If you get the depth of that curve just right, so that it's half the thickness of your metal, then it bends on the center line, and you end up with the inside surfaces exactly the edge of your curve cut. So there's almost no bending allowance that you need to make.
If you practice more,
I have, it's slower. So this, I cut out the box in about an hour and a half. So, yeah. But it's a worthy investment of $30. So, anyway, you can pass this around.
So we can make the carbide kit laying down there, that would.
Yeah, we can pull it out and fix it.
Oh, that's all right.
Okay.
Yeah, I just,
You know, like the metal cutting carbide blade costs about $14. So that's the main metal fabrication trick. The layout for the box, I'll do a little sketch of the box here. This is your, well, I suppose I should talk about the dimensions we want for the box. So these bricks are, they have that module size. So we're going to stack them up to make the little square. So you end up with a 6.5 inch square by 4 inch deep kind of ring module. So that's our so they're 11.5, which basically a square, 11.5. And then the depth is 16. So
So is that just for best use of your materials? Is it to help with the, because you said the coils mean something, so is that the best use of the
that
space?
was,
Or
that was all based on I settled on that dimension because that's roughly as big as an even heat knife making film, their small model. It's like a 6 or 7/10 of a cubic foot is the basic even heat. This one's a little bit smaller, but it's what you can fit out of a minimum number of bricks. Because if you go much bigger, you need some couldn't just use a single brick across the top. You'd need to have a joint and some more support structural mortaring it together. So this was kind of picked to make it the simplest shape, because you could just dry fit it. You don't need any pinning or joint or mortar of these bricks. So that gives you this 11.5 outside dimension. The inside dimension is about 6.5 high and 6.5 wide. So on this was all cut out of one sheet, and so it's this rectangle with 11.5 strips scored into it, and then another, it's like 5. So these inner lines are the score lines that I cut with the circular saw, and then you get rid of 2 of these panels, and you can fold that up into the box and fold the 2 ends closed, and that makes the back of the box. And then I kind of pieced together the door out of those other scrap chunks. But the back, so on the box, there was a long rectangle, and I pulled up the 4 sides, and then on the, imagine this is the back, then these 2 doors, or 2 5.5-inch wide pieces fold in to make the back. And then it's basically just tacked together with TIG rod, and it was really hot, so I didn't clean the rust off, so I used only one stainless TIG rod. So that's the main fabrication of the box. You want that dimension pretty tight to your brick dimension. So I can show next how to do some of the shaping of brick here.
And you could get different dimension bricks right there.
There's a couple of other, I know there's one common module that instead of 9 by 2.5 by 4, it's 9 by, or sorry, either 4.5. It's 4. But
Now, looking ahead with some of the thickness, you're also going to be carving into it to set your elements. So you
Right.
don't want to go too thin
yeah,
because
you
you
want
need.
as much insulation as possible.
If you go to any brick and have to fire brick, they have the full
Yeah.
brick and they have the stretch brick on the side.
Yeah. The other common one I've seen is instead of 2.5, it's 2. So they're a little bit skinnier. But I think you want that full thickness because you want the most insulation you can. Ideally, probably the most economical and what will get you to get up the fastest would be these bricks and then add an inch of K-wall on the outside, inside your enclosure. Then it gets wobbly. So,
Now, the wobbler, the concern is more about shifting it or moving it. So if you have it in place, it's not so much of an issue, but
right, so these are just, in general, they're pretty delicate. The brick is so crumbly, and the wire, after you fired it a few times, it oxidizes a bit and it gets pretty brittle. So the less vibration and bouncing and moving it around you can, the longer it'll last. So I tend to make it and put it somewhere and then don't touch it. Especially if you were going to insulate the outside of the K-wall, you want it to be, you kind of put it in its final resting place and then use it. And when you move it, things are going to shift and you'll have to assemble the bricks back together.
now I notice yours doesn't have it, and it might not be necessary. But you mentioned mortar earlier. What about castable refractory or lining the inside to any of that? Or
That could be doable, though all the castables I'm aware of are much higher density. I don't know exactly the density of these, but they're not very heavy.
well, it's more like putting a layer on just to
Yeah.
protect the crumbliness of the
Hot
fire
base
brick.
layer.
Just as
That could be doable, but then you've got to keep that off of your elements or work the depth for the elements or something like that. So, don't eat the dust, don't breathe the dust from these bricks. That's probably the first thing I should talk about with the bricks, the safety issues. They have lots of potential to make fine silica dust, which is a known carcinogen. So you really don't want to breathe this dust. When I'm working it, I usually use keep a filter going in the room and wear a respirator mask now we'll just say that the element is going to be a 3/8 diameter outside coil. So we need to make a 3/8 diameter slot in the edge of the brick. So for that, I just basically, you've got this much workable area, and these are at about the center third indication. So they're 2 inches up and 2 inches down. And the easiest, put back that one, pass it around.
Right there.
So this one is going to be the center portion. So I'm just going to show that there's three, this kind of makes a ring, and there's 3 of those rings inside the box.
Do you actually need water to make a dry joint?
These are all dry joints, so
Okay.
if you want to use mortar, and I've used in the past, my other one, it has a bigger lid that has some joints in it, and they use kind of a regular silica-based fire brick cement, and it's worked okay. It doesn't, like, it really doesn't have any tensile strength to it at all. So that lid is held together by the steel frame that presses it together. So if you need to use a mortar, that's probably what I use, is aluminum silica-based fire brick.
I got bricks easy to get here.
The Kinney Brick Company has all the
Okay,
time.
break it down.
Yep. So this one's gonna be the bottom of the floor section. And so we need to trim off part of it. So you just make a mark all the way around with a square. Pencil works just fine on it. And then, the only real trick to cutting it is you start in and go a hacksaw depth. And then I'm going to angle that, I'm going to keep this, the far side at that depth. And then here where I can see this line, I'm going to guide it down so that I end up with a diagonal cut. And then you flip it around and work down the other face. So you just want to, that's the main trick, following the line carefully. And you go pretty slow, so I'm using my finger on the top of that blade just to make sure I keep this side of the blade up at the top of this cut. Because it'll drift if you're not keeping your eye on it. So then I go down, so now there's a diagonal cut like that. You work the blade out carefully, the dust can kind of compact in there, and these are fragile enough that just the dust and pulling it quickly can crack it. So again, think a strong grain cracker. So now we can go all the way down, rotate the brick, go all the way down, and I follow with my eye on this side of the line.
Better to cut that outside.
Well, outside of the letter, you really don't want to breathe. The best thing is to be wearing a
Yeah,
respirator.
but it would be better outside with a mask, correct?
Yes. And then in the back, you have to go away. This one has a washable heat filter in it. Anyway, that's a cut. You can get a pretty, it doesn't take too long to get fluent at cutting right on your line. I've seen videos of people using like a router or something like that, and the amount of dust is amazing.
Have a stand for a quarter band, stand it up. Look like a
Porta band, oh, bandsaw blade,
Yeah.
portable bandsaw blades.
You probably could, but well,
they make the stands for the quarter band.
yeah, I think I can get straighter cuts with the hand saw.
So I know it's
Notice
been,
I vacuum the faces, but since it's so portable, spaces or you're gonna have dust migrating everywhere. So this little offcut chunk will be kind of the corner fillers. This sketch here is like a cross section of what we're building. So these are the side bricks, the top, these are pillars at the corners, and then a center piece that we just made that cut for at the bottom of it. So that's what I'm showing building, is one of these ringing segments.
Is it what we pick up the deck in the rest of the day?
Yes, you really don't want this dust going
So-
around because it definitely carcinogenic dust. So you want to go to fairly extreme lengths to not breathe it. So just a few cuts gets you the basic ring shape. If you have corners that are chipped and stuff, those can be on the outside surfaces where the insulation matters the least. So that's kind of the main cuts. Now the next part is making the grooves. So this one I've laid out, here's where the floor comes up to on this bottom line, and then these two are where the grooves are going to go. The top line is 2 inches down, the bottom one is 2 inches up from the floor. And we're going to create 6-inch grooves. So then we just do it on the drill press, the slow speed drill press, and it creates a bit. You just drill that hole right through it. So you're going to put your 3/8-inch hole so there's about a 1/16 of an inch between the edge of the bit and the face of your brick. So that's a 5/16 over from the edge is where these two marks are. Centered right on the groove. So a little groove. That on the drill press, you're welcome to come take a peek. There's no big trick to it.
I'm gonna stand up.
So this is just a 3/8-inch bit.
So once again, for those of you in the back who might not have heard, lots of ventilation, HEPA mask while doing the work, although he wasn't doing it here, HEPA filter in the vacuum cleaner to collect the dust. The dust is carcinogenic. Please make sure to stay safe while doing that. It's one of the 2 major safety risks.
Press down flat on that table so that you get a square tool. If it's off, then it'll rupture through. Choose it up. The only real trick is to evacuate the dust while you pull your peck drill. So you need to drill it every not make sure so we can clear that dust. If the dust builds up and backs in that hole, it contracts right now. now we've got two holes basically where the element's going to go, but we have to get rid of this little lip. And so I just take the hacksaw, cut through basically on these, or a little bit in from these guidelines. And it does not take much. So that's kind of exposed the slots. And then to clean them up the rest of the way, just take a piece of 3/8" hole thread and use it like a file. And you just kind of start in a slot, wiggle it back and forth. So it's all fresh and out all the way in. And that's about all it needs to clean up that slot. Pass this one around, I'll leave the one hole finished and the other one is. So that's basically the big trick. On the other one, there's up on the front bricks, you have to make kind of a U-shaped groove. There's a little bit of trick to that. So here where the element turns this corner and it's not a straight groove all the way through, I'll show doing this U-shape on the other one. So I've got my square set to the 6.5-inch depth. That's the inside of those bricks. And I've got a couple of marks in Sharpie on here so that all the measurements are repeatable and consistent. Because the biggest, every time you make a mistake in your layout here, you just throw away 6 parts. Unless if you make your groove in the wrong spot, you can probably flip it around and use the opposite side and just leave that groove on the outer surface of the brick instead of the inside hot surface. So it's better to make yourself a jig, a guide, some kind of witness mark on your measuring equipment so that that can be avoided.
What's that old adage? If you're going to do it more than 3 times, make a jig for it.
Yeah, usually even more than one. Especially when you're trying to talk and show something at the same time. Okay. So now that one's laid out just the same as our first brick, but an inch from the edge. I'll make another mark, create the map, and then just kind of like drawing a radius. This doesn't have to be precise. Going by eye is just fine. So that's kind of the shape we're going to go for. So the main trick is I'm going to drill down just to about here and then stop. And then drill in just a little bit to do that little vertical connection segment. So, back. So this is making a U-shape. And again, you just keep a lot of downward pressure, make sure all those water comes right off the table so the bricks get really flat. So this saw I'm using a short piece of saber saw blade just to clean out the top web of these holes. And then the alternate trick to file goes the rest of the way. And you can kind of vertically use it to open up this U shape the rest of the way. Deep enough for the element to make it in there. That's a U shape. So this would go, there's our floor. That fits in there like that. This piece would be on the other end. You can see if we're measuring it accurate, the grooves line up from one brick to the next. And that's basically all the brickwork tricks that you need.
Now it looks like the back only has one, so do you just go along the top bar?
Yes, so that's getting into the element length calculations next.
Ah, okay.
So, so anyway,
You make 4 of those?
in the kiln there's 3 of these rings, so you'd make 6 of the, well, you'd make 2 of them with the U slot, 4 of them with the double slot, and then the back have 2 bricks with a single slot at the top, except the slot stops perfect. So, one at the back. The back ones get a single stock slot. So basically the same technique as making the U, except you don't make the U. You just go without that depth and stop. And that's, the back one will fit something like that. And it's only connecting the channel at the top across the back. So our element, maybe easier on the kiln itself. The element runs, it's not a good view in there. But the bottom slot, it comes in the back, up the bottom slot, up that U to the back, across, along the forward, along this top slot in this wall, down the U, and back, and out the back on the other side. So that's the shape of our element. It's going to be. This is my little copper wire jig thing. So this is, the way I approached it was first calculate roughly how long you need the element to be for the correct wattage. Then I made the bricks. Then I made this little copper template by basically just fitting the copper wire in where the element is going to be, bending it around the curves, and then you can measure how long the coil you need. There's little tape marks of where it penetrates through the back wall. So this gives you an idea of the element length, and it comes out to be, I believe it's like right around 58 inches. So just kind of bend the wire, followed along the table roughly. We'll just shift it that way, but anyway, so that's roughly how long I need. So that, following along the, kind of like the traveling wheel, so there's our 58-inch coil line that you get from measuring the slot for the piece of copper wire. Now, we can talk, so that, are there other questions about the brick forming techniques I showed you? So that's most of, basically just making the slot, the U-shape and the stop slot are the only real tricks.
And then the doors just fit it in the door?
The door, just, I stacked up the bricks, measured this little strip, put some little curves, and bent this. And you want really as snug a fit as possible. So it's probably, I made it basically an exact fit, and that's a little tight, so then you sand or file the surface of the bricks just a little bit until you think you can squeeze it in without cracking it. And kind of spring the metal open a little bit so that it has a little bit of, it's trying to clamp that a little bit. And yeah, nope, this is just simple fabrication on the inside when you're fitting the brick. Some places there'll be tack welds, and I just take the little pull thread and file a little bit of the corner of the brick off there to a little relief where, like if there's a weld on the inside of that corner, I'll relieve the corner of the brick a bit so that it's not mashed up just against the spot welds and preventing it from sitting against the surface of the sheet metal. So, but pretty straightforward fabrication. You just want a nice tight fit. If you're less confident on your abilities of getting that exact dimension, you can always make this like 1/16 of an inch small, and then the bricks, I need to take the show, but they file really easily. File or just glue down a piece of sandpaper on a board, and you can take off material surprisingly quickly. And then you can horse around and file the surfaces down to get a nice snug fit. So that's pretty much the brick fitting. Now we can talk about the element side here. There's kind of a rule of thumb. This kiln's internal volume, I think just over a third of cubic foot. There's an online spreadsheet which I can send that has a lot of the, can do a lot of the calculations for you. Okay. So this is about a third of it. It's like 0.35 cubic feet. If the internal surface area is also important in the calculations, so there's kind of a rule of thumb for 1 watt of power per square centimeter of surface area. So this one's about 2,800 square centimeters of the internal surface of this brick volume. And that's the inside chamber, so the 6.5-inch square by 13 deep. So you want a 2,800 watt of power to heat this up pretty quick. You can certainly do with a lot less power, but it may take you an hour to come up to temperature. This one, I think I tested it exactly from full to working heat, but somewhere like 15 to 20 minutes. This one is designed for 240 volt. You could run it on 120 volt, but you would need to size your element differently. If you run this element on 120 volt, you'll get a quarter of the power. So you only get, like 800 watts or something like that, which can take quite a while, and you start losing, the rate it loses through the insulation might be too fast to really get to the high end of the temperatures you need, which is 16 to 1700 for most heat temperatures. So centimeter gives you the total wattage. So that's kind of the guide, and that is 2,800 watts of power. We just use Ohm's law, and to find your 2,800 watts, that gives us the amperage of something like 10.4 amps, something like that. And then if you calculate, so then you've got 240 volts times divided by your current will tell you the resistance of the coil will be. Something like that, and it comes out to I think it's 20.5 ohms is the resistance you need to get that current at 240 volts. So that tells you how much wire you need. The wire comes in all different sizes. My other kiln uses 16 gauge wire. This one, when you think about the layout, how long you can make a channel in your kiln, that kind of tells you what size wire you need. If this kiln were much bigger, you could have you could fit a 10-foot long element in there. So you could use a heavier gauge wire to get that wattage you need. This one works out pretty well with 18 gauge wire. That one is 0.5 ohms per foot of wire. So you can put these calculations in the spreadsheet, and it tells you we need 36.7 feet of wire to get 20.5 ohms of resistance. The resistance rating of this wire is pretty consistent. It goes down slightly as the temperature elevates, but it's not by much. The room temperature resistance of this element will change by about quarter or a third of an ohm up to about 1,800 degrees Celsius. So it's not a huge change. There are tables to look up that compensation that get involved. In general, you want to use the biggest wire you possibly can to get the most life out of the element. It's oxidizing. Every time you bend it, that little surface oxide cracks a bit, and then exposes the metal, and so that crack can propagate through there. So the more meat you have to your wire, the longer it'll take before those cracks go all the way through and create a high resistance spot will burn through. So 16 or 18 gauge wire is a pretty appropriate choice. There's another rule of thumb for the size of your wire. This is a little diagram of a coil, and you want the small diameter is the diameter of the wire. For 18 gauge, that's 40 thousandths of an inch, or about 1 millimeter. The rule is you want the diameter of your total coil to be something like 5 to 8. So big D is 5 to 8 times smaller. That means for a 1 millimeter wire, you want maybe an 8 millimeter coil with something like that. And if you have, the reason for that is if you have a really skinny wire and a big loop, it gets flexible. It's like spaghetti at the temperature. So that loop will collapse. So you need a small, tight enough wire that it can be self-supporting so that element doesn't slump over and touch the neighboring things and reduce the resistance and that. So that 1 watt per square centimeter of the surface area and your coil diameter of 5 to 8 times the wire diameter is kind of the two main constraints. So we know this length, so it's 36, 5.7 feet, something like that, the wire will give 20 ohms of resistance. So we need to figure out how long of a coil will use up that 36 feet of wire. And that you just divide your length by the thickness of the wire diameter. So 36 feet divided by 20 thousandths gives you like 480 individual coils that you need. If you're, well, that depends on the manual size. So this inner therefore outer diameter is, in this case, you can get it at 9 millimeter. And so if you use a 1/4 inch rod on the inside, that will give you about a 9 millimeter outside diameter of the coil. So then you just divide the length of your wire by the circumference of that. So you have a mandrel and your wire circumference of one ring. Luckily, the spreadsheet will do most of it for you, but you figure the circumference of one coil and divide that, and you figure out the number of coils you need. Then I basically decided I was deciding between a 5/16 mandrel and a 1/4 inch mandrel, and the 1/4 inch mandrel is closer to the 5 to 8 inch. So that fixes the diameter. Then you find the circumference of each coil, which is 0.91 inches per ring of wire wrapped around a 1/4 inch mandrel. And you divide the 36 feet by 0.91 inches, and you get 486 coils is how many. So then to figure out how long that coil needs to be, you divide your 486 coils by the thickness of the wire, and that's 19.4 inch for the length here, L, is our coil length. And that's the heavy math part. So, but I will certainly email, or we can put in the 12th email this spreadsheet, which is pretty. You basically plug in the wire diameter, the wattage you want, and it spits out how long the coil should be.
Yes,
So,
please provide that to the club so we can send that out. And
anyway, so this is a mandrel. It's the only fancy part of this jig for building the whole thing. It's a piece of cold roll. We don't want to use hot rolls because the rough surface makes it hard to get the wire off of. And then 2 pieces of plywood. One of them you drill a 1/4 inch hole in there for your mandrel bit, and then screw it together to another piece of plywood. And this one, in the same location, it's got a 3/8 inch hole. And then you make a little tangential saw cut to that hole, and that's what guides your wire. That's the whole jig. So, this down pretty quick. And then the jig goes, it's kind of cool. So this is the easy wire. There's a little cross hole drill in each of our rods here. So, put that in, start winding it. And at first you want some pretty loose wraps. And this, you're going to unwind these to make a little tail where you connect it. So try to do 8 or 10 inches of really loose, wide wraps. This is just to get the wire around the mandrel so you can slip it on your blade. So it's going to, the cross hole goes through the big 3/8 hole. And out this direction. That keeps the coils tight pressed against each other. They can't fit out to a 1/4 inch side of plywood. So that's what makes a tight coil is a little bit of tension. You do have to make sure there's enough wraps on the rod that the friction holds it. Otherwise, you will pull the rod out of the middle of the coil. But then the wire goes in and the coil comes out. And there's my stop mark.
I understand demo being demo and where we are, but is it easier to put that in the post vise, or is it better to have the tension?
It's definitely easier to plant this in a vise. Then you gotta rig up something that kind of keeps the wire from feeding in without thinking. So, demoing is a little easier with stuff in the air. But especially if I was gonna do more than one, I would set up a vise plant and stuff.
And the bar that you set on earlier, I think I heard, I don't know how many people in the back heard, that was just to add tension onto your spool to help it.
Because this is so springy that the whole come on spool to make a rat's nest. So the bar just adds a little friction. So then you should be able to unscrew it and slide it. And coil over it. Let's see if I got the start marks were really long. Let's see. Look a little bit shy. So we're going to put it back in, and I'll make this a little bit more, but for the demo, so you can check that length to get it just right. For the demo, we'll just use and that 18 ohms doesn't matter. For 20.5 ohms, you can play it up or down one, and it's not going to be the end of the world. So I pull the wire out of the little cross hole, and then the rod should slide away. Leave the long tail, like I need to do so. And there's her coil. So you stretch it slightly, and then test it with an ohm meter to see if it's got the correct reading. You stretch it a little bit so that the coils aren't touching each other and short it. Alright, so it's saying 20.4 ohms, so we're 0.1 ohms off on the target. So that's good enough.
That just means it'll heat up slower, correct, from your earlier
So
description?
yeah, so instead of like 20, well, just using ohms now. So you do 240 volts divided by your 20.4 ohms, and that'll tell you how much current you draw, which should be around 10 amps. So then I'm just going to bend the tail up a little bit, and you want probably, this is the tail where this is our back tail. So the coil will be, it'll be coming out this bottom slot, and then the tail is going to go through a hole in this back brick. So I want to know how long the tail is and what's my connection. So we want about 4 or 5 inches of tail. And in order to make sure that this skinny wire doesn't burn up where it's penetrating the brick and it can't radiate the heat out, you double it up. So you fold it over on itself and twist it so it's double. And this small straight section is still going to put out the same amount of heat per length, but it's, since it's not coiled, that length per linear inch is much less. Or that heat per linear inch is much less. So it won't melt. Most of this is done with very little blacksmithing. wrapped around the rod and it's twisty. You practice that. You guys feel this part, it's the long, expanded part of the coil, and feel how stiff that wire gets from the work. So we want to kneel it a little bit before we twist it, or you can have it crack. So you give it a little bit of a kneel before making a tail on that end of the honey mandrel.
Yeah.
And then somebody to help pull. So the last step is, so our slot length is 58 inches, but we just made a 19-inch long coil. So something doesn't match up there. You have to, if we tried to heat that element there, the wire, there's too much heat and it will burn out that element very quickly. So you've got to expand it, you have to stretch it. So that there's a spacing between those ring elements of the coil. And the guide is you want that to be somewhere between, I think the space should be 1.5 to like 3. So we're going to expand this coil to like 3 times its length. So you'll have a space of 2 millimeters in between each ring. And that gives enough room for the heat to radiate out without overheating the neighboring coil. So it's all about surface area and how much radiated surface area on that coil is. And they call that surface factor, and that's just watts per surface area unit of the wire. And if you stretched it, you've got less wire area per length, and you've spread out the heat over a larger area. So you're not concentrating it too much on that wire. So that's, when you hold it, you're just going to stretch it like a spring. If there's other questions about the wire pattern, it's pretty fun when it makes that nice coil like that. And it's a dead simple jig, and it does the job, and you just save $50 by wrapping it up by yourself instead of trying to buy one that probably doesn't quite fit the dimension you need.
So
Where are
just,
you getting your wire from? Is there a supplier for it?
So this 15 gauge wire is on Amazon. It's $20 for 100 feet, and you could make almost 3 coils. You can certainly do 2 coils out of 1 roll, so it's about $10 a wire. It's even cheaper if you buy 250 feet at a time if you want a lifetime supply. So,
And where do you get it?
Amazon has it. You can order it directly from this wire Optin place, and they're a bit cheaper. WireOptin.com.
Looks like a welding coil. Is that
It's aluminum. It's Canfo wire, which is, I believe, it's basically a stainless alloy. It's like 22% chrome and some aluminum in it, like 6% aluminum. So it's fairly stiff wire, but it provides a lot more resistance than the steel wire, and more the chrome lets it survive at the high temperatures. It's good for up to about, they say 2,300 Fahrenheit, but the higher you run, the hotter you run it, the faster it degrades. So, like that. So that's. So, it's not going to, well, you know, this little bit, porch, and you will get it so that you can see a little bit of color in here, and go over this area to take the color. And this removes a little bit of the work hard made. But like I said before, the wire, once you heated it, you also start oxidizing and getting more brittle. So you don't want it to get a really bright heat. And I don't know if this will harden at all, so I've just been letting it go. It seems like it would be like a shock. So then, we'll let that cool for a second. For fitting it, I've talked a little bit about making this copper wire jig, and that's helpful in knowing where to put your head. So use it to measure for the coil length, and it's good for fitting these first bends, because you want a pretty close fit between the coil and the groove it's in. Like this back, the section across the back wall will be here. And if it's too short, if this middle section is too short, it'll be hanging out with this groove on the corner, and it'll sag. If it's too long, it'll want to bulge out in the middle. So you've got to fiddle and stretch and get the coil to match the groove length pretty closely. Once you get it roughly bent and fit in there, then you attach it with just some pins of the same wire. Just cut some little straight segments and push them into the brick. So, that's well enough. So I'm going to kind of unwrap this wire to get it straightish again. And that's how we make the tail on this side. And you don't want to just stretch it because that'll keep the twist in the wire, put a little more work to it. So I'm basically unrolling this coil. And then same thing about a 4 or 5 inch tail. Bend it over, twist it up, and trim it off. You can do it with that drill, but plenty of drill windings. Okay. Now, if we have somebody, so now we're just going to stretch it. Previously, I got this mark on the table. So you put that thing here to the table. So then it stretches like a spring. Here's our mark, but it's got some spring back. So you've got to overstretch it until you get real close to your mark. That's it. So, and now it's nice and compliant, flexible, and slinky. And then a slinky, yeah. So now I'll start getting it forming using my jig, or just to show a bend or two. So previously I built a kiln without discovering this copper wire trick, and this makes all the difference. And you can take like an hour of fiddling around, screwing around, putting in bends, and taking them out. But if you have this little copper wire jig, you know just where to go. Now the trick on a bend is if you just bend it, the inside of that corner, the wire will get compressed and you'll lose that spacing. So you want to rotate it and stretch it. So most of the spacing, so the spacing on the inside of that bend is still consistent. The outside can be way more spaced out. So you don't want to compress the inside of the bending wires too close together, or that'll be a thing where you get too much energy density and the wire clips. So there's one bend.
So you kind of measured to the middle and then started doing the bends
Yeah.
rather than starting
It's
at
like
one
bending
end
a
and
piece of
going.
stock. Yeah, I found the center of the wire and starting at the center of my jig and going to work out toward the end. Because it's easier to stretch or compress at the end than it is in the middle, because then you've got to trace that more or less wire back through all your bends. So you work from the center to the end of your coil. So just following the proper wire guide, putting into that. So that's probably, I may start turning it on and we can talk about the PID controller while it heats up, but I'm not going to make fully form this entire coil because you guys have seen the bending wire before. But we'll do that. Take a look, have it around, compare that. So we'll just show putting in another pin because it's the location where it needs to be more pins. So for that, just going to see since I have some of this slightly thicker 16 gauge wire. Straight, so now cut these like an inch and a half long and push it
Now, do you have to worry about that pin in contact or too close or a good distance from the coil, or?
It's probably in a bridge part of the coil, but there are not enough pins that it makes a big difference. And it's more likely that the coil sagging out of its slot will destroy it before reducing the resistance from the pin in. I've had a couple where the coil just sagged out and then it sort of, I don't know exactly what it did, but it burned itself up and made a little pretty sag. But when my first kiln had fried the wire element and it was like $75, and that was sad when those shorted. But if it's half hour to make and $10 a wire, it's a lot more reasonable. One more, if you want to look, you can see the back, or on the right top coil, it's kind of sagging out of its groove, so I'm going to put a pin in that one too.
Probably best to stand right there.
We can put pins in all day. This one's a lot long enough that it doesn't fit for the rest of the demo. Okay. So, I'm going to turn this back on and make sure it's getting hot. Very good. So there's a little, we can talk a bit about the controller. These guys used to make, it's called a PID controller, which means it's a proportional integrating derivative algorithm. It basically means it compensates for drift. So there it's starting to get hot. We'll close the door, let it cook. They take a set point and a measurement value. And the SV is the set value, PV means the process value. These use a K thermocouple to measure the temperature, which these are also pretty inexpensive. You can find this, you want one with pretty thick wire. This is a K thermocouple, so it's chromo, aluminum, and Constantine is the name of the alloys. And they're just two rods of those alloys, and they weld. You can TIG, you can gas weld, fuse the tip together. So if you're really shooting for the economy, you can buy both thermocouple wire and just solder them together, or fuse them at the tip together. And those two different alloys create a microvoltage at different temperatures. And it's proportional to the temperature. These will read somewhere between, I don't remember the negative temperature, but I know they go somewhat negative below freezing and up to around 2300 degrees Fahrenheit, or 1300 Celsius. And they're pretty stable. This one costs like $8, and it has this nice ceramic mounting base on it. That's its input. It comes with a little cheesy, teeny thermocouple that will burn up right away inside the kiln. So you just replace this thing's K thermocouple with the bigger one, and connect. It has like on the side here. It's got a little chart that shows where you wire. It needs AC power. It can be 128 to 270 volts. It has the input for let's say TC for thermocouple, and those do have a polarity. There's a positive and negative because one alloy makes positive voltage, one voltage comes out negative. So you've got to make sure the polarity is correct on that. But it's all, the wire is color coded. You can use They come with this little short thermocouple, and you can connect thermocouples to anything as long as you use more of the same thermocouple wire. These little brackets are not thermocouple alloy, but it doesn't matter because if you have a joint, say this is cheese grade Chinese stainless steel, the chromo aluminum element will make a small micro voltage with that stainless steel, and you don't know what it is. And as long as you use another piece of that same chromo aluminum alloy, it will make the exact same opposite voltage, and they'll cancel each other out. So as long as you keep the same same type of alloy wire from on your negative all the way up to your sensor, then they average out. You can use whatever metals you want to join them, wire nuts, whatever. So you connect the thermocouple, and then it has one other set of wires that you need to connect to the thing that actually does all the work, which is a solid state relay. And that's essentially just a really big transistor, or probably a FET transistor. And that's this whole kit with the PID controller, the SSR, a little thermocouple, and a heatsink for the SSR. These are all available for about $20. So long ago, I made my own using a microcontroller and programmed the PID algorithm and stuff, and it's not worth it anymore when you can buy this for, you know, this is probably more expensive. So this is probably $10 for the controller. And so you wire that up, thermocouple into it, power into it, and its output goes to the output terminals of your solid state relay. And those also have a polarity of positive and minus. And it's something like a low voltage signal, like 5 volts. And that just tells this when to turn on and off. So this is just a fancy switch, but instead of a mechanical relay that will wear out after a lot of cycles, this one is good for, they would say 1 million cycles or something, but usually they'll die somewhat before then. Usually when these die, they weld close instead of open. So there's a chance that your relay can just turn on and stay on, and it'll melt your overheat and melt your element. But you wrap your own element, so it's not too big a deal. The trickiest part about these guys is the instruction sheet. So they come with 4 buttons, and that's it. But there will be a table in here of parameters, like P17, P16, P75. There's P codes, F codes. The big trick on this one brand, and I can again send the link to this particular one, is in order, when I first set this one up, we're up to 1260 degrees now. So that's cooking along pretty good. It's only been about 5 minutes. So it's getting there. And when I first set it on, I set it for maybe 1,000 degrees, and then wanted to bump it up to 1,600 once it reached that, see if it would get up to a hardening heat. And it was topping out at about 1,250. And I was like trying to figure out how to change the parameter for the maximum temperature of the controller. But you can't. And I eventually measured it and realized that it was 1,200 Celsius, not Fahrenheit. So you just have to switch the parameter to change to Fahrenheit. That's actually the only. So the first thing to do to calibrate them is called auto tuning. It takes the PID control is the proportional means that if there's a big gap in the set temperature you want and the temperature is at, it goes proportionally full on to try and get there in a hurry. If it's a very small gap, it goes very small pulses. This relay only pulses on and off. The controllers can handle a situation where you could go 50% or 75% on or off, but this is just on-off control, but it changes those pulses with a duty cycle. So, you know, it's right now when it's still trying to gain 200 degrees, it's just on all the time. When it starts getting close, it's going to start pulsing that relay on and off, so that the set temperature comes up and matches, or the actual temperature comes up and matches that set temperature. without going way over it and then way below it. So the algorithm is smarter than just, is it below the temperature, turn it on, if it's above it, turn it off. It learns the heating rate and the cooling rate of the kiln and will pulse appropriately to make it, ideally it will go right up and hit that set value without overshooting or undershooting and wiggling around. Without it knowing any of those parameters, it's kind of a crapshoot. So the first thing you do is when you get close, there's this second button says it's a down arrow, but it also says AT, and that means auto tune. So you hold that. It doesn't improve your singing, but it will improve the speed that it hits that target temperature. So you hold it until it starts blinking, and then this will go through and tune those parameters to more closely match and limit the overshoot and undershoot. So that's the first thing you do, is do that auto tune. You set a value close to where you want to be working. Like if you want to be hardening at 1500 degrees, set it for 1500. When you're close, have it auto tune, and it'll go up and above a few times, and then set those parameters. And you should only have to do it really once unless you've changed something dramatically. The other thing on here is we want to change it from Celsius to Fahrenheit. Right now it already is in Fahrenheit. Okay, so it stopped blinking, so it actually thinks it's auto-tuned well enough. So to change the other parameters, you hold the set button. And it'll say P. And this first one, this is the hard part, it's a little bit like South Park. You have to get this thing to respect your authority. This first parameter, P00, is called the data lock. I don't know. And you have to give it class 2 authority by typing in 18. So, you push set again. Well, it starts on 0, which doesn't let you do much. So now, what it's on 15, now it can go to P31, which apparently is Celsius Fahrenheit. That's set on 1 for Fahrenheit. If we change this to value 0, then it should be reading in Celsius. Anyway, there are a lot of these kind of esoteric codes. Well, you can also switch off. Exactly. It remembers the settings of the power cycle. So now it's saying 804 instead of 1500. So it's switched to display to Celsius. But that's the only real trick for this controller is that first P00 you have to set your class authority to 2 to be able to change it. Other than that, that's about it. The one other safety concern, I should say, is this, when it's energized, there's, even if the relay is, so the wiring on it is pretty simple. The 240 volts comes in, one leg of it goes through that solid state relay, and then to one end of the coil. The other leg just goes to the other end of the coil. So if you think about it, even when that solid state relay is out, the coil in there is energized at half the voltage. So even when it's not on, the coil is at 120 volts. When the relay is on, then the coil is at 240 volts relative to ground. So if you're standing in a puddle with tongs poking metal onto that coil, you will get shocked if the switch is on. So it's important for safety to run this through a double pole switch to turn off both legs of that current. Otherwise, you've only turned off one side of that coil and it's still at 120 volts to ground. So, most of it, I have a little sample here of 1095 and 4130, and we can flip them out and typically I let it soak or see if I can put it. Any questions? I'll put it back in there.
So assembly-wise, you build the box, you build the coil spacing, you put all the brick in. When did you add that external box that holds the brain?
I did that before, I built almost all the steel before putting the bricks in, because welding and drilling on it will generate a lot of dust and maybe chip or crack the bricks. So you want to build the whole enclosure before you fill it with bricks.
So
And
you,
that's actually kind of the fiddly part, is figuring out where to drill your holes so the wires pass through. On the back where those metal running,
'cause I figured
I
that's
just
a
used like
fiddly.
an electrical handy box, and screwed those on the back, and they have an opening in the back. These are box extensions, so the back's open, and you're welcome to come around here and take a look. So those are just screws to the back, and that's the pass through for the coil tail. And the other piece of hardware we use are these little ceramic insulator blocks that just have a screw terminal inside and some ceramic insulation. And that uses some 12 gauge copper wire on one side and a coil element tail just clamped down in the ring. And that's really the only one actually make. You can't solder it because of the heat. You can't use wire nut, so it needs to be a high temperature crimping connection. So you can see this little ceramic block here in the back, and you can see where the element wire is supposed to put a hole and it's back.
You haven't any problems with that little bit of tail of the element wire, getting your insulation going, and there's enough free air moving through those.
Yeah,
wires, so
I
it doesn't
sort
matter.
of, you can feel some heat coming out here because that tail does put out heat. So you can like poke these knockouts slightly in to let it ventilate a little bit. Typically you're not going to run this more than an hour at a time. So anyway, but you can, on this side that's not open, you can put your fingers here and feel the heat coming out.
So that's applying the two holes in the back.
Yep.
What I was going to get to on the side is the temperature, the thermocouple that goes in.
Yeah, that
How do you
you can also
position and
see.
drill that effectively?
There's also just, so that I just positioned it, basically just drill a half-inch hole for this, and I positioned it, the top, the ceiling brick is up here, so I positioned it about halfway between the, so, and we changed the length of the thermocouple so that the tip of it is what's doing the reading of temperature. So you want that kind of in the center. If it's really close to an element, it might read a little bit higher than the average in the center.
So you drill the hole in the brick before installing it, and then drill.
And there's a cutout on the inside this little control housing.
That's what I was wondering, if you did the cutout first and then aligned and drilled into the brick, or did the brick and
Well, I
then
figured
went one way or the
I
other
put the thermocouple hole first, and then marked where I need that hole for the.
with the brick, and then pulled out the brick.
Anyway, that's
So does it heat constantly until it reaches the set temperature, or does it heat up
Well,
and then
it'll-
take a break and heat up? So it doesn't blow
there's
up?
sort of a sketchy little diagram here. It'll heat constantly until it gets pretty close, and then it'll start
Ramping?
pulsing to ramp down so it doesn't overshoot. But this is
Okay. And what makes it ramp down? What is that? I mean,
Well,
it's
that's
the
the
PID,
PID algorithm.
but what about in the old type stuff? There was
Uh-huh.
it wasn't a relay, it was, I can't remember what it was called.
I think old ones may have used like a bimetal strip controller or something, but I think, I mean, they've been digital controllers for quite a
Yeah,
while.
right.
But this kind of shows a graph of if this is your set temperature and this is the actual temperature measured, it goes up, and by tweaking those parameters, you can see this one probably has too much overshoot, whereas this one is getting pretty good.
So you were talking earlier about after it runs a while, it learns how to
If
do
you
it
do
better.
the auto tune feature,
Okay.
so that's where you have to do that hold it down and say auto tune, which is different for every different brand, but they all have some kind of auto tune thing. This one has sort of a little flow chart of the sequence of how you run it. So this is, so to set a temperature, you have to push the set button, and then you can go up or down. And set again. So now the set bell is 858, it's currently 816. This little indicator shows if the relay is on or not. So it's on right now because it's got to jump up 30 degrees to catch up.
So what's it at now?
Now it's, well, it's Celsius at 30, and I just bumped it up 40 degrees, so now it's going to 850.
Okay. So you built one before? Is that what you said?
Yeah.
And what did you heat treat it? Tools? Or?
I've done tools and knives and glass pieces, and it was kind of the wrong shape. It was a lot wider. It was, I think it's a 13-inch square, but only 6 inches high, and the top hinges open. So having a front door is nice because if you hinge the top open, all the heat, it loses its heat way faster.
It also burns your arm
And it
when you
also
open
burns
it.
you reaching in and out. So,
Yeah, it's a nightmare opening.
so a front loading door is good. The fancier commercial ones, they have a door that will lift up like this on some parallel linkage arms, and it moves up like that. So the hot face of the door interior isn't there radiating at you, but it also takes up a lot more space vertically. So this one, I have like a little dinky shelf under my drill press it will fit on, so I don't want a door that, it can't fit a door that
Right.
opens vertically.
Okay.
What's your lifespan on the heat elements?
Um,
Assuming you don't tear on the back of your truck and beat on it,
Right,
you know, put it on the shelf. and
The
leave it.
other one that it has a 16 gauge element, and it's a little bit lower, it's like a 19 ohm, so it's a little bit higher wattage, it's like 3,100 watts or something, 200. And I had one element die after about 6 months, but it sagged way out of its slot. And after I replaced it, it's been going, I don't know, 12 months without any issue, and I use it maybe once or twice a month.
For $10 a wire,
Yeah.
not just the bed.
Anyway, so that's,
What about the other parts, the PID, the controller, the relays?
so that's all. Same one, first one. No, we're done on that. Yep. Anyway, so on this type, it's probably the safest way to operate it by shutting off the double pole switch whenever you open that door to reach in and get it. So you turn off the controller, you turn it off, so that there's no chance you're going to zap yourself. It actually remembers the temperature it was set at and turn it back on, and it's going again in 5 or 10 seconds. So it's not like it's losing much, and when the door's open, that's losing your heat more than, the most significant temperature loss. So. Anyway. Huh?
Where do you source the electronics?
These are just on Amazon. I'm going to put this extra electronic set in the iron in the hat. If somebody thinks they'll actually get to build one, I'm happy to put all that stuff in iron in the hat. Is anybody thinking of building a heat treat oven? Yeah? Yes. All right. Somebody will take it. That's thrown in the iron in the hat. This thing is a kit. It's just the controller relay. The relays do generate quite a bit of heat, so they need to be on this heat sink with thermal conductive grease. But I think they come with a little yeah, it comes with a little thing of thermal conductive grease that goes between the heat sink and the relay. Long ago I had an SSR die because it didn't have a big enough heat sink. I just put it on the back of the steel box and it was not enough. So your thermal grease goes in there between the relay and this wooden box. Yeah. So really getting pretty commodified, these little PID controllers, and pretty economical.
So we've got that. You talked about the safety with. So major safety, of course, is the dust from working with those. You talked about the electrical safety of having it plugged in. Anything to consider when plugging into outlets, walls, power drain?
This needs, so this should be drawing 10 amps. You need to design it for the size of circuit you've got. plugging it in, even if you design a 120-volt one, plugging it into a home 15-amp circuit is probably not a great idea. So I would recommend, this should be fine on a 15-amp, 240-volt circuit, but most of the ones I use is a 30-amp. You just need to make sure your conductors are stock. This is all electrician related stuff.
Seek a professional to make sure.
A professional electrician install, check your outlet for the proper load, and you need to follow. Anyway, probably the biggest warning is this is in no way UL certified. If you run this in your house and it burns down, the insurance will not pay for your house.
Or your shop.
Just making sure we get those quality statements in here. But
Yeah.
with
So it's drawing 10 amps right on the.
with that level of insulation, and you said you have it under your drill press, the box itself doesn't get that.
If you run it for an hour, it'll start getting a little bit warm, but it's not. Really not too bad.
Now, sorry to put you on the spot like this, but quick and dirty math, because yeah, I know there's a spreadsheet to help with the math and all that, but if you wanted to make one, you said it's down to the square footage, so if you make it shorter but deeper, say if you wanted to be a swordsmith, you could do that at about the same size. If you wanted to double the size, would you just double the coils and the wire kind of thing, or would you want to do the full calculations
Basically
again?
go for that 1 watt per square centimeter. So that's the best guide, or somewhere around, I think it's 4,500 watts per cubic foot of volume, basically. Unless you get a really weird shape. If it's some kind of cubic rectangle solid, that'll be about right. If you want really long and skinny, you're going to have more surface area per volume. So if I were to make a really long skinny sword treating one, you could probably get away with a pretty similar size one. Maybe just do one pass along the walls instead of two. And it may take longer to heat up, but it's probably not doing a lot of swords.
But it also seems like one of the big things you need to consider is, as you said, you need the temperature gauge sufficiently distant. So even though right now it looks like there's a lot of empty space up top, that's also where you have your temperature gauge to be able to allow it to address.
I know a good resource for heat treating is knifesteelnerd.com. He does a lot of videos and articles, and he has several books on general heat treatment, but he has one talking about gradients inside an electric kiln, and it's really less than you expect. Like, I think he has an even heat, and it's pretty similar physical proportions, and I think his spread from like putting a thermocouple at the top versus the bottom, where you probably expect the biggest gradient, or from the back to the floor, is about 15 degrees Fahrenheit. So it's pretty uniform inside there. You get a lot of convection that stirs things up.
He has a YouTube channel also.
Yep.
He's got couple of really good books, Knife
Yeah.
Steel Engineering.
I've read most of those books.
Have you read the one about the history of knife making?
Parts of it that,
I haven't-
like on the steels,
I haven't
some of
bought
it
that.
was interesting and some of it was could use editing, or maybe it's interesting if you go to steel or company or
Yeah.
a lot of
He gets into a lot of
Do they have that going to the medieval, or is it mostly just
No,
No,
like-
it's
modern
okay.
steel making.
from the 70s up.
Yeah.
Okay.
Yeah, his father was a knife maker, Devin Thomas. And this guy's a metallurgist. He took his interest in making knives with his father.
Yeah.
And so he's got it. Watch his YouTube channel. It's an excellent
Yeah.
resource.
And that's the knife making nerd?
Laren Thomas.
Knife steel nerd.
So where did you get all your resources when you started this?
Well, the biggest one was this calculator spreadsheet, which was from. I'll share this too. I have like a little flipping.
Is it written in PhD mode or in regular uneducated person mode? Can
No,
understand.
most of it was a knife making website.
Oh, okay, good.
and I'm trying to remember his name.
Layman's terms, layman's terms.
Yeah, layman's terms, okay.
So this, it was, a lot of it was from DC Knives, but that, he passed away like 2 years ago, and his site was down.
Oh.
So I had sort of an archived version of it, and someone recreated the spreadsheet from his data that was on the website, but it has a lot of its element sizing calculations. Stuff. So, with that said, these are probably ready, we can punch them. I'm going to turn off the switch before you reach in on and overload it. And we should have a red piece.
What kind of steel are you using there?
That's 4140 and the 1095.
Okay.
Now do be aware, since it is soft fire brick that is on there, you can slowly damage it depending on how evil you are when you put your knives or sharp objects in there. So please keep that in mind when working with this.
Yeah, actually, that was, other thing I usually do is I make, out of scrap brick, I'll cut one relatively thin, like half thickness, and make kind of a little pallet. So I'll take this and drill a hole and put several stainless steel welding rod pins in there, and then you can slot your blades in there. And if you made a little fork and have two other holes, you can kind of slide this in and pull your little brick in and out like a pallet. And that helps keep the scale and cruft off of the bottom of the skin. And it's easier to load, especially if you're doing multiple things at once.
It can also totally be sacrificial, but do remember if you're sliding soft fire brick on soft fire brick, it can also generate dust, so keep that in mind.
And in general, I keep it closed. You open it, 4 times a month with all doors open, basically outside and in the garage.
If you decide to use something like kiln shelving, I'm assuming it can last longer, but that does affect on how well it will heat because it's like putting hot fire brick, so it'll take longer to heat up and everything else.
Like New Mexico clay, they call it kiln furniture, and they have all kinds of shapes. This hard, and it's ceramic. I'm not sure if it's aluminum ceramic or different, but it's much more dense than these. It's like dense fireplace fire brick, but they have little vertical stands. You have half-inch thick shelf boards. And it's probably a good idea to get a piece of that and put it at the bottom as a sacrificial protective sheet. That will also cut down on dust.
And since we do have a couple of young smiths, would you quickly describe, because you've said heat treating and whatnot, what all do you do in this for, is it just tempering, hardening? Can you give that full little song and dance for some of the newer people that might?
So these are 2 little coupons we just put in there. This one is a piece of 1095, a pretty common carbon, high carbon knife steel. This is 4130 or chromoly, which is for stuff you're gonna use, dies, punches, race car roll cages, anything that you want to be extremely tough. When you take the steel, so this whole thing is for getting your steel up to the austenitizing temperature. Steel is mostly iron with some carbon in there. Normally, it's a body-centered cubic structure where, if you imagine a cube of steel atoms, iron atoms, you'll have one at the corner of each cube, and you'll have a carbon atom sitting in the middle of that cube. When you heat it, everything expands a little bit, and it switches to what's called a face-centered structure, where that carbon atom moves to the middle of the side of that cube. And it just has more thermal energy, more room to move around. That's where that carbon is happier at that higher temperature. So that happens at the critical temperature, or the Curie temperature of the steel, which is somewhere around 1400 Fahrenheit. It varies plus or minus, mostly plus 100 to 200 degrees, depending on the alloy. When it changes that crystal structure, it goes from normally being a perlite and iron structure to what's called an austenitic structure. And if you cool it rapidly, some of that carbon doesn't have time to move back into the center of the cube as it's freezing. And it gets trapped there and creates lumps and irregularities in that crystal structure, which basically makes those crystals harder to slide across each other. And so it makes it much, much harder. You'll go from 10 times the strength of the metal, but much more brittle. So that's, you quench it and you harden it into a structure called martensite. And that's what makes tools hard, knives hard, and doing it in a really controlled way lets you get the best properties out of your steel. It's easy to do it by eye and quench, but you'll probably miss by 50 degrees. If you're doing it in an oven, you can hit it by 10 degrees. And going over it, over your critical temperature is more of a problem. That leads to bigger crystals and less strength. So that's basically what happens in the crystal when you treat it. But for either of these steels, an appropriate hardening temperature to get it to do that change is probably 1525 to 1575 Fahrenheit. And then cooling them, and then the 1095 would need to be tempered to reduce its brittleness somewhat, probably at 400 or 500 degrees, half an hour. The 4130, probably again 400 degrees for a half hour if you want its maximum hardness. If you want its maximum toughness, it should jump up to about 700 degrees to reduce the brittleness. So these pieces I can probably, the 1095 inch I can just snap them at some time. The 4130 will need to be on which, anyway.
You use it for that. You'd also use so you can harden with it. You can anneal with it,
Yep.
and
Yeah,
with this you just turn it off or
It'll
let
happily
it
do,
slow shut
yeah.
down.
So it takes, if we turn it back on, it'll tell us the temperature it's cooled to. So it's down 500 Celsius, and we can measure that. But it probably takes it longer to cool off than it does to heat up. So that's, compared to my old one, I'm pretty pleased with the ratios of this one. It looked like it got up to heat in about 15 minutes. My other one is more like 30 minutes.
So would you explain, you made the coupons, would you explain why you were talking about snapping them? Would you explain about the grain structure?
Right,
and everything?
so I can go ahead
I mean, we do have vices nearby, or if you go to watch him snap it because you are new to this, understand that he is snapping metal. There are potential of
If you
small
wanna
flying
come
bits
watch,
going by,
Need
so
safety
protect your eyes.
glasses.
Yeah, because if you send a little chip out, I'll just snap these in half.
Totally not trying to avoid us getting sued for getting in trouble. No, never. Oh, you should have seen the one that her son sent me earlier. This week, let me see this link. Oh, I totally want one, but I also want one that's able to do helmets and body armor. No, it's the one that you open the door and it has a little scissors tape on top with cookie baking over the board door. So James, when are you gonna make me one? You already have one.
So here's the little coupons. So we hammered on this is the 4130, and it took, even with that in the temporary, it took nearly 90 degrees of bang before it. The too hot. But this is kind of big grain to me. And it snapped almost instantly in the tongue. So it's all a big balance between ductility, or how much you can stretch it, versus strength and how hard it is.
Now, again, for some of your new people, he was using materials, he knew what they were, what he bought, whatever. If you've been here for a lot of our other demonstrators and some of our favorite people, they'll talk about junkyard steel, stuff that they go out and they find. So they will create those test coupons, and then they will see how it reacts when they do it, because some they expect to harden underwater, some under oil, some different things. So even if it's known, it's best to test it with your processes so you know what you're working on if you can. But if it's unknown, definitely test it, because you don't want to invest a whole lot of time making a tool that you then find out can't do what you need it to do. And if you get the chance to come to our Rob Gunther demonstrations when he decides to describe stuff like taking mild stuff and using super quench to get the hardness and things like that, that's kind of a different thing, but it's all the same concept depending on what you want to do. This is just a very, very good, unique tool for what you need if you want to get into doing this more often and in a more controlled environment. You can do all this heat treating with a forge. It's just a matter of you take a lot more risk because you're not dialing in and controlling the temperature all the time. You have the possibility of running it. This, it's almost like your oven. You set it to that temperature, it's going to be at that stuff. If you set the metal in there long enough, it will soak through and it won't heat beyond the temperature you set. Meanwhile, if you're in the forge, you can run your edge all the way to where it's going to really do damage on it. So keep that in mind. It's a more advanced tool, but we hope this is something that you enjoyed seeing. Sorry if I took over.
Yeah, and so any other questions? And if there are details you want, please, I will write an email that can hopefully go out in the club with links to all these goodies needed for building it. But please email me if anybody's got more questions.
So roughly how deep are you? I mean, like, how much? That was my question. What's the cost?
Yeah, so I got, not including the demo ones, I bought 20 fire brick, and they're $6.50 each. So it's $140 a brick. It was a 32 by 48 piece of 16 gauge, whatever that is these days.
This was 25, 30 bucks.
Yep, so probably 30 bucks a steel. I had this cord that's probably 30 bucks. 20 bucks more of switches and handy boxes.
So you're 225, 250 bucks. And a comparable size even heat is like 1,500, 2,000.
2,000. Yeah. So I think you could probably 350 would be more than adequate. You could probably get under 300 easily, depending on if you have to buy any tools or stuff. So you can, probably 10 to 15% of the cost of a commercial.
And essentially the same result.
Anyway, and you can size it to what you need. A lot of it depends on, they make them for knife makers, and they make them for like research labs too. And other than that, you're kind of on your own, or you're this is third.
I will tell you right now, you can usually find the parts of these made because pottery shops love getting them, but when the elements burn out or the electronics go bad, they quickly abandon them.
Exactly.
And so sometimes you can get secondhand a bunch of the shelving or the fire brick that's already cut out, but fitting it to your needs. That's where I think a lot of your work is very important, because
being able to roll your own element to fit a kiln that you find somewhere can be very handy. And you can, the hardest part of that is just measuring what wire gauge they use. But you can also basically measure the length of the slot, the diameter, and those that's probably enough information to construct, to reverse calculate your element size. So you know the diameter it's got to fit in a slot, and you know how long that slot is. So that tells you roughly what the wire needs to be and the volume of it will tell you roughly the wattage. Pottery kilns tend to be lower wattage because they're not concerned with heating them quickly. So they're fine with them taking 8 hours to make a temperature, but I don't want to pay for 8 hours of electricity to heat a night.
Also, not that I've been at community colleges that were operating on shoestring budgets, but yes, you can use some of the mortar that he was talking about to repair them. You can use kiln shelving to reinforce them. It does affect how efficient they are, so do balance yourself on how soon you want to make or repair a part versus quick and easy fixes. Because the efficiency, as he's talking about how long it takes to heat up, at first you think, oh, an extra 10 minutes isn't much. When you start talking hours and you see that electricity bill slowly go higher and higher, that's when you really have to think, how much time is this benefiting me versus taking, I mean, he built an entire module here in less than 30 minutes. The coil took less than 30 minutes, so repairing it isn't that bad. But take notes so that when you have to recreate it, you know what it is without having to redo all the math or figure out what you did 2 years, 3 years, a decade ago. Just saying. But please do share anything with an email. We'll make sure to get that out to you. Any other questions or comments?
We got the spreadsheet if you guys want to take a look at the calculations that goes through.
What's the hottest you got it go?
Yesterday I accidentally hit 1250 Celsius before I realized it was Celsius. So that's
And you said that shortens the life of the coils, right?
probably
Running at that.
So that is 2280 Fahrenheit. Just about. Yeah, you can start doing casting.
Yeah, you start melting wire at that point, right? 'Cause is there a benefit to like this wire over the old micron? Price?
I don't know exactly. I think it's price, and I think this may actually have a slightly higher temperature range.
And the micron's more expensive, so
Yeah.
it's more expensive than the lower temp. Or to go wrong for $20.
Yeah.
So let me start off with thank you very much to our great demonstration. We appreciate it. Very, very knowledgeable. Please let us know if you want more demonstrations like this in the future. Usual sales pitch. We need ideas on what you want to see, so please tell us so we can try and get that for next year. Next, we do have our usual potluck. Please help yourself, get your food, things like that. I will be selling Iron in the Hat tickets in about 5-10 minutes. I will probably set up somewhere easily enough to find me so that we can get that going. Also, please take a look at our 2 beautiful candle holders that I believe are on display for the trade items. I do believe the Iron in the Hat are some of the tongs, a cross, another candle holder, some components.
PID controller, relay kit, and a roll of the 18-gauge wire in the Iron in the Hat. So if someone's gonna go for building it, this will get you most of the way.
One more question, like, so is this like a weekend project that would take you about?
I hate to admit it, but I started building it on Wednesday. And it took most of the day Thursday, finishing up left. So probably a good 12, 15 hours.
That also.
A lot of that is fiddling around with how exactly do I want to configure the electrical conduit wiring stuff on the outside.
And that was also building the outer case, correct? Or was that already
Yeah.
built?
Yeah.
So cutting, scoring, bending, welding, all that.
But I have to say, I've never used one of these metal carbide blades in a circular saw before, and it's really nice for cutting sheet metal.
We got that going. Please remember to sign in before you leave. Sign in and make sure we know how many people made it here today. Also, there's the sign-up sheet for the state fair. Please help us out in the state fair. Reminder, state fair next month. Please support the local club. We will have our table there. We are looking for all the different items for that. Also, if you're interested in helping educate the youth, please talk to Jim or myself, etc. Let us know so we can make sure to get that going. Otherwise, thank you very much. We do have additional questions, but thank you for being here.